In section 5.4, we're going to set up the theoretical machinery that we need to do something called modular arithmetic, which is something that applies to a lot of cryptography methods. So we're going to start with a definition. Given any two integers a and b, a non-zero integer c is a common divisor or common factor of a and b if c divides both a and b. Now remember what c divides a and c divides b means. C divides a means there exists some integer, let's call it m, such that a equals cm. And then c divides b would similarly mean there exists some integer n such that b is equal to c times n. When we have the list of divisors of two numbers and we figure out which divisors are in common to both numbers, there's definitely going to be a greatest one of these, which we call the greatest common divisor, and we use the notation GCD of a and b. Since every integer is going to have some kind of positive divisor, it's fair to say that the largest or the highest or the greatest common divisor would actually be positive. So it's not just a convention, it's also something that makes sense if you consider lists of numbers where you're guaranteed to have at least one positive number. The greatest number in that list should be positive. So for example, we have 24 and 42. If we were to list all the divisors of each of these numbers, the ones that would be in common to both would be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Among them, 6 is the biggest, so 6 is the GCD of 24 and 42. And then similarly with 12 and 32, here's the list of common divisors. So the largest one in that list is 4. So before you continue, I want you to verify that these statements are all true. Practice a little with this notation. Think about generating lists of divisors, in particular common divisors between two numbers. And then think for yourself about why the greatest common divisor of 3 and 5 is 1. Now I know we talked about this in class, but it doesn't hurt to review it. So give that a try. Pause the video for a moment, and then we'll move on. Now let's consider the special case of 0. Why is the greatest common divisor of 0 and 3 equal to 3? Well, remember that 0 is divisible by any non-zero integer. If you take any non-zero integer, let's call it a, then a divides 0 because why? A divides 0 for any integer a that's non-zero. Remember our notation, z star means all the non-zero elements of a set. So why is this true? Because 0 equals a times 0 plus a 0 remainder. So because a divides evenly into 0, every non-zero integer is a divisor of 0. But what are going to be the common divisors between 0 and a number like 3? Well, the common divisors are going to be all the factors of 3. And what's the biggest factor of 3? Well, it's 3. What's the biggest factor of any number? It's going to be itself, as long as it's positive. If it's a negative number, then the biggest factor would be the absolute value of that actual number. And that explains also why the greatest common divisor of 0 and negative 3 is also going to be 3. Okay, so take a moment to think for yourself of an explanation as to why the greatest common divisor of 0 and -8 has to be 8. So generalizing what we've been talking about is this theorem that for any non-zero integer b, the greatest common divisor of 0 and b is absolute value of b. Remember a moment ago I said something about absolute value? Well, here's that general statement. The largest positive divisor of an integer, a non-zero integer, is going to be the absolute value of that integer. Why absolute value? Because you have to consider the case where b might be negative. So if b was like -72, what's the biggest divisor of -72? Well, it's positive 72. In other words, the absolute value of -72. If b were a positive number like 64, then the greatest divisor of 64 would be 64, which is the absolute value of 64. As we said before, all non-zero integers divide 0, so really you're looking at the list of the divisors of b. Okay, so now that we have that fact, we're going to make some quick observations and move on. So the greatest common divisor of a and b is going to be the same as the greatest common divisor of b and a, because you're looking at the list of factors of both numbers, seeing which list is in common. That list will be in common regardless of whether you consider b or a first. And then GCD of a and b is the same as the GCD of plus or minus a plus or minus b. The sign of a and the sign of b doesn't affect which is going to be the greatest positive divisor common to both. Because as we mentioned, even if you have a negative integer, you're going to have that its greatest positive divisor is going to be the absolute value of itself. And we know that GCD is also always positive. So just for simplicity, we're going to throw out all the cases where our integers are 0 or negative. So from this point forward, we're just going to focus on a and b being both greater than or equal to 1. And again, also for simplicity, we're just going to assume b is greater than or equal to a. Okay, so building on that assumption that we're going to be working with, we have the following theorem. Let a and b be integers such that 1 is less than or equal to a, which is less than or equal to b. If we apply the division algorithm to a and b, in other words, if we have b equal to aq plus r, where r is non-negative and it's less than a, then the greatest common divisor of b and a is exactly the same as the greatest common divisor of a and r. This is probably the most central theorem of this section. So just so we don't have a ton of letters floating around for the proof, we're going to call GCD of a and b d, and we're going to call the GCD of a and r e. D is necessarily a divisor of both b and a because it's the greatest common divisor, so it's definitely a divisor. That means we can write b as d times some integer and a as d times some integer, and those integers respectively are x and y for the sake of this proof. What is r then in terms of what we've just defined? Well, if we solve this equation for r up here, r is equal to b minus aq, and doing some substitution, we have that equals dx minus dy times q. We can factor out a d from both of these. X minus yq is going to be an integer because it's a combination of multiplying and subtracting integers, which makes it still an integer. That tells us that d is a divisor of r. So d divides r. Again, we've written r as d times an integer. That's exactly what d divides r means. So that means D is going to be a common divisor of R and A. Why is that? Well, we know D divides A, and we just showed D divides R. So that means D is a common divisor of both R and A. Well, we know that E is the greatest common divisor of A and R. So since D is a common divisor, it has to be less than or equal to the greatest common divisor of A and R. So absorb that for a moment, and we're going to continue with the proof. Okay, what we're trying to do is we're trying to show that D equals E. So the strategy that we're using is show that D is less than or equal to E, and then show that E is less than or equal to D. All of that together would imply that D equals E. We want to show that D is the greatest common divisor of A and R. Okay, so continuing with the proof, we know that E, which is the GCD of A and R, just by our definition, for the sake of our proof, E is a divisor of both A and R. So it's a common divisor of A and R. That means we can write A as E times U, R as E times V for some integers U and V. Again, we're applying the definition of divides. So if we take the original equation that related A, B, and R, we have that B is equal to AQ plus R, and if we do some substituting, we get that A times EU plus EV is going to equal, once we factor out the E, it's going to be E times the quantity AU plus V. And again, A times U plus V is going to be an integer because each of those, A, U, and V, are all integers. We're combining them with multiplication and addition, so it's still going to be an integer. That means E is a divisor of B. So that means E is a common divisor of both B and A. Because we just showed, well, since E divides A and E divides B, that makes E a common divisor of B and A. But we defined D to be the greatest common divisor of B and A. So that means E has to be less than or equal to D. So again, looking at the strategy we talked about a moment ago, this combined with the fact that D is less than or equal to E, which we showed in the first half of the proof, gives us that D equals E.